Hello and welcome. My name is Kagwe Munro and I'm your mechanics teacher. In this video, I want to look at the complete solution to the mechanics paper of the year 2004 May-June session. This being a very long video, you might want to skip to specific questions in the video. So just hover your scroll bar, your cursor over the scroll bar rather, and there are timestamps that I've put there. Each timestamp directs you to a given question. So this one will help you to save time. Although I will really appreciate if you play the whole video, even if it is very long, because the moment you do that, the concepts that I'm talking about are going to be installed in your store of concepts very, very well, because they build upon each other. For instance, I might be talking about question number 2 and refer to something that I mentioned in question 1. So it is always important to play the whole video. However, feel free to skip to any part of the video because you might be revising for a major exam and you might be in a hurry. So again, welcome. So let's go straight to the first question. What do we have here? Of course, we've got a rod and a ring, and the information we have, let me get the correct color. We have a ring of mass 1.1 kilograms. It is threaded on a fixed rough horizontal rod. The reason they've mentioned the word rough is so that we can know there is frictional force between the ring and the rod. A light string. I've dealt with light inextensible strings before, so play the previous video. Better still, you can enroll in one of my courses at Udemy called Mechanics 1, where I've dealt with these concepts extensively. I've put the link to that course in the description of this video below. So, a light string is attached to the ring and the string is pulled with a force of magnitude 13 newtons. So this is 13 newtons. It is one of the forces acting on the ring at an angle alpha below the horizontal, where tan alpha is 5/12. The ring is in equilibrium. There are several things they have mentioned here. I want to deal with this aspect here where they give an angle as a trigonometrical ratio. When they do that, there is a method which they want us to use to solve this particular question. For example, when this angle is given as tan alpha is equals to 5/12, we are supposed to use a right angled triangle like this. Just get a right angled triangle. We are going to refer to this angle here as alpha. Tan alpha is usually opposite over the adjacent. So the opposite to the angle is that. The adjacent to the angle is 12. And if you use Pythagoras theorem, you'll be able to get this value, the value of the hypotenuse. This time, it will work out to be 13. You can go ahead and clarify that the hypotenuse of this triangle is 13. So this will be 13. How do you do that? You do the opposite squared, which is 25, plus the adjacent squared, which is 144. When you have 144, you add 25 onto it, you're going to get 169. If you do the square root of 169, you get 13. That is how you get that. So from here, you'll be able to get the other two trigonometrical ratios. You can be able to get the cosine of alpha being adjacent over the hypotenuse. This one will be 12/13, and maintain them as ratios. Don't go ahead and work out that angle like I've seen some students doing. Once they are given this, they work out the angle. Don't do that because the examiner does not intend that you follow that direction. How about sine alpha, which is opposite, which is 5/13? The reason why I'm saying this is that you're going to see how they cancel out very, very easily. So remember, cos alpha is 12/13, sine alpha is 5/13. So one of the things you're going to take away from this video is this. When an angle is given as a ratio, do not work out that angle. Rather, draw the triangle here and use Pythagoras theorem to work out any of the sides, and then keep them on the standby because you will need them. We will need to resolve this force vertically downwards and horizontally to the left, like that, when it comes to that point. So I was talking about this and why it is given. So the moment you see this in any of the mechanics questions, remember this is what you can quickly do and put these ones on the standby because you will need them. So the ring is in equilibrium. Again, we know what happens when a system of forces is in equilibrium. It means the resultant force on that system is zero. Resultant force is zero. This further means that after resolving all forces in two basic directions which are perpendicular to each other, you will be able to equate forces that point in opposite directions comfortably without worrying about other forces which are acting. Again, I'm going to demonstrate this in a moment. The next thing is we are asked to find the frictional component of the contact force. Look at that long term, frictional component of the contact force. What does that mean? It means that there is a contact force here, and that contact force has a frictional component. The other component it has is the normal component. Look at this, the normal component of the contact force, frictional component of the contact force. In Mechanics 1, they will always use that full term, frictional component of the contact force, normal component of the contact force. So get used to it. So how do we calculate the frictional component of the contact force? One of the ways that we can be able to do this is if we know the coefficient of friction and the normal reaction, we can be able to use that equation. Now, if I go to the last section here, I've actually been asked to calculate the coefficient of friction. So this may not be the method. But just in case you write the equation there, just allow it to remain there. Put a comma or go to the next line. Yeah. Let's see. Now over here, it's important that you resolve this force in two convenient directions. Sometimes they won't tell you the directions in which to resolve. They won't do that. Sometimes they will do that. In this case, they have not even suggested. It's up to us in Mechanics 1 to realize that the two most common directions that we are expected to deal with is horizontal and vertically, or along the incline and perpendicular to the incline. Those are the two situations that are very common. Here, I can be able to see that because this one is not an incline, the rod is not inclined at any angle, it's horizontal. It's best to resolve horizontally and vertically. So I'm going to resolve this so that it points vertically downwards like this. I'm going to get the component of this downwards. I also get the component of this horizontally like this. These are the two components of the 30 Newton force. The two components must always make 90 degrees with each other. Since this is alpha, then the component which makes an angle with the force itself will take the trigonometrical function cosine. So this will be 13 cos alpha. Now let's see how I get that. 13. Look at cos alpha. It is 12 over 13. See how easy they cancel out to give me a very simple answer. See that? They cancel out very, very easily. And that is why you don't go and work out the angle of alpha. You express it as a ratio so that somewhere those values will be able to come to cancel out so comfortably. The examiner has done it in such a way that it will give you a very easy way when it comes to dividing and multiplying. And the same is this component here, because this component will be 13 sine alpha. 13 times sine of alpha. This one will be 13. Sine of alpha is 5 over 13. 5 over 13. And you can see this one gives me 5 newtons. Again, very easy. You'll be able to work through this question very, very easily. Now, so this is one of the forces acting on the ring, and its two components are 12 newtons that way and 5 newtons this way. Let's look at the weight of the ring. The weight of the ring is somewhere at the center of that ring. So I'm going to draw a line from that point pointing vertically downwards. And this will be the weight of that ring. And its weight is mg. It will be 11 newtons. 11 newtons. So at this point, from this video, let me just erase this, because I've got exactly what I wanted. Also erase that, but I leave those. I'm going to leave these ones as they are. This for the sake of creating more space. So it acts that way. So the ring appears to apply a total force of 16 newtons on this rod. So the rod is going to react to that and push the ring upwards with what we are referring to as the normal component of the contact force. However, if this rod was smooth, the ring will slide in this direction, and because it's rough, it resists that, and there will be friction in this direction. These are the two components of the contact force: the normal component of the contact force and the frictional component of the contact force. Now this ring is in equilibrium. Notice that I have resolved this force horizontally and vertically downwards, so it disappears from the equation, and the only force I have is this one, this other one, this one, and this one. Those are the forces which are acting on this system. In fact, the forces acting on the system are just how many? I think there are three. There is the weight of the ring, there is the tension in this string, and there is the contact force. The contact force has got two components, R and FR. This tension has got two components, 5 newtons and 12 newtons, and the weight is 12 newtons. Those are the three forces acting on the ring: the tension, the weight, and the contact force. So after resolving, I'm now in a position to come here and say, what is the frictional component? Okay, first of all, we have ruled out the use of this equation here. But in an exam, since you will be writing this information on paper, once you've written it, don't bother to erase. So the frictional component of the contact force is this. The resultant force on this ring is 0. That means after resolving the forces acting on that ring or that system in two directions which are perpendicular to each other, we are going to equate opposite forces. In other words, the forces acting to the right is a frictional component of the contact force. The forces acting to the left is 12 newtons. And that is how I get the friction component of the contact force. Let's look at the normal component of the contact force. The forces acting upwards is R. The forces acting downwards is 5 newtons and 11 newtons, which means 16 newtons. At this point, I must sound an alarm. For those who have done very few questions on a frictional force and they are used to this situation, they're used to a surface and an object on the surface and the weight of the object and R, and they end up saying R is equal to W. The normal component of the contact force is equal to the weight of the object, which is true for that particular situation. If we apply a force, maybe at an angle on this object, this force will have a component this way and a component this way. You can see that now there are two forces tending to lift the object, while there is only one tending to pull it downwards. In this case, R will be W minus this component. So understand that it's not always the case that this will be the case. Be careful about that. So, and this is such a situation, many students will make this mistake of thinking that R is equal to 11 newtons, forgetting that actually there is this other force here which must be added onto it. Now, given that the equilibrium of the ring is limiting, it's limiting when we have this word being told that the equilibrium of the ring is limiting, it means they are giving us the permission to use this equation. Friction force is equals to mu R. In other words, mu, the object is just about to move and the friction force acting on it is maximum. That is when you use this equation. You don't use it just any time. This one will be friction force divided by R. The friction force is 12 newtons. R is 16 newtons. If I divide here by 4, I get 3. I divide here by 4, I get 4. It's 3 over 4, or 0.75. And that is how you work out that question. Again, what is the take from this question? Remember, I have to repeat this information over and over again for you to be able to understand some important concepts in mechanics. One is the way the angle can be given. If it is given like this, then we know what to do. The other one is the idea of the normal component of the contact force. This one here, normal component of the contact force. It's not always that it is equal to the weight of the object. It may be equal to the weight of the object. It may be equal to a value greater than the weight of the object. Like, for example, in this case, you can see R is greater than the weight of the object. Or it can even be equal to a value less than the weight of the object. It can also be equal to 0. So, be very careful. Now, how do you know whether you're moving in the correct direction? These are the pointers that I would give. When you have a situation whereby the forces given, they are not horizontal, they are not vertical, they are not along the incline, always understand, you have to resolve them. What is the importance of resolving forces? We resolve forces so that we can treat each one of them or a group of them independently from the others. For instance, observe that when I'm saying R is equals to 11 plus 5, I'm not bothered with how much FR is, because when you're given forces which make 90 degrees with each other, they can be treated independently of each other. And let's go to question 2. Before we go to question 2, I'd like to show you something that I had done. I had already shown the resolution of these forces on this diagram, but I felt that if I just show you this diagram, it will just it may end up confusing you more. So, but it's basically what we have just done. This first arrow is the normal component of the contact force. This one is the frictional component of the contact force. This green one here is the weight of the ring. This one is the vertical component of the tension in this thread, and this is the horizontal component of the same tension. So it's just a neat diagram, and it talks about what I've already talked about in the previous slide. Let's go to the next slide, which gives us a question number 2. And here we are, a system of forces. System of forces. Just by looking at that, I'm highly excited because I know I'm required to resolve, and when I resolve, I may be required to combine a few forces in a particular direction, combine eventually to get the resultant force. Anything can be asked. Like for instance, in the 2003 paper, you've already gone through it. There was a question that was asking us to calculate the components of the resultant force. The components of the resultant force. Remember, the resultant force has got how many components? 2. And these 2 components are always perpendicular to each other. So let's see what we are required to do here. We are given coplanar forces. Again, what are coplanar forces? These are forces in the same plane. Co means same. Planar comes from the word plane. Coplanar means forces in the same plane. So coplanar forces of magnitude 250, 100, and 300 newtons act at a point in the directions shown in the diagram. The resultant of the 3 forces has magnitude R and acts at an angle alpha anti-clockwise from the force of the magnitude 100 newtons. Find R and alpha. Let's see what they are telling us. They are giving us that these 3 forces, they have a resultant which is R. It acts at an angle alpha anti-clockwise from the force of the 100 newtons. So we can say that this is where our force R is. This is where our force R is, R. And it has an angle alpha from the 100 Newton force. So they're asking us, calculate R and calculate alpha. This is not a complicated question. All I need to do is realize that this R has a component in this direction. It has a component vertically. First of all, it has a component this way, a component vertically, and then when they are combined together, they give me this using Pythagoras theorem. So let's see what we need to do. So in the process of getting the resultant force, if there is a force which is not in a standard direction, by standard direction I mean, is the force horizontal or vertical, or is it along the incline or perpendicular to the incline? If it is not in any one of those directions, you need to resolve it. And you can see this the case with the 250 Newton force. So you need to get its component this way. and you need to get its component this way. And because this is 70, this one will be 250 cos 70. Of course, this one will be 250 sine 70. Let's see what that gives us. So we've got 250 times the cosine of 70, 85.5. So this one will be 85.5 newtons. How about 250 times the sine of 70? This gives me 234.9. 234.9 newtons. Yeah, 250 times sine of 70. So what is it that we now have? Forget about this force. Now we have this force, this one, and this one. Now we are going to add forces which are acting in the same direction to get one force which acts in this direction, and its value will be 100 plus 85. It will be 185.5 newtons. And then we are going to get one force which acts vertically. So will it be vertically upwards or vertically downwards? We can tell by looking at this value and this value. Since this one is greater than this, it will act vertically upwards, and its value will be 300. We get 300. We subtract 234.9. And we get 65.1. 65.1. You know what this means is this. This is the vertical component of R. So R in the Y direction is that. This is the horizontal component of R. R in the X direction is that much. So this resultant force has two components, this component and this component. So how do we get the resultant force if we are given its two components? We put the two forces head to tail. So I'm going to have Rx like that, and then I'm going to put Ry here. So this one will be my Ry, whose value we know it is 65.1 newtons. And now the resultant will be from the first tail to the last head. There. This new force is now our R. Is this R. And this angle is the angle that we've been asked to calculate, alpha. So you can see that I can get alpha using the tangent of that angle. So alpha is equals to the tan inverse of 65.1 divided by 185.5, and that is going to give us, so I get the tan inverse of this one, 65.1 divided by 185.5, and I get 19.3 newtons degrees. 19.3 degrees. So I've answered the second part here. How about getting the value of r? Getting the value of r is very easy because I just need to use Pythagoras theorem. 65.1 squared plus 185.5 squared, everything square root. And so I'm going to have 65.1 squared. I add 185.5 squared. I get that. Then I get the square root of that answer, and that will give me 196.6. 196.6 newtons. And it is just as simple as that. Nothing complicated. So when you're given a system of forces, don't panic. In fact, you should get excited because the methods are always the same. And if they deviate from the norm, what they have always done, it will be easy to identify where they have deviated, and you will quickly discover that trick. What I'm appealing to you is this. When you're solving these questions, always treat that question as being unique. Be very careful when you are reading through. Watch for some of the things which give you clues in the question. Look at the diagram, the arrangement of forces. Are they horizontal and vertically, or along the incline or perpendicular to the incline? Or is there a force which is deviating from that? If there is, then you know what to do. Are they talking about a resultant force, meaning that the system is not in equilibrium and there exists a resultant force? Or are they talking about the system being in equilibrium? Or are they interrupting that process somewhere in the middle? Like, for example, in the paper 2003, they, instead of asking us to calculate the resultant force, they asked us to calculate the component of the resultant force in a particular direction, in the direction PQ. Go and look at that video once again and see how we solved that question. I believe it was question number 2. Again, use the scroll bar there at the bottom to simply go to the question of your choice. So that's what I can say about question number 2. Let's go to question 3. So what we have here in question 3? A velocity time graph. You remember what we must remember when we have a velocity time graph? Yes. The area represents displacement. That is the area under the graph. For example, this area for the first 10 seconds represents the displacement covered by this object when it's moving with uniform velocity. While this area also represents displacement. One of them will be positive, another one will be negative. We will see that when we come to the question. So remember, the area represents displacement. The gradient will represent the acceleration. Armed with those two, you should be able to know what to do. So let's go to the question. A boy runs from point A to a point C. He pauses at point C, that is, he stops. And you can see the velocity is 0. He pauses for 5 seconds. And then walks back towards A. You see, he's walking back in the opposite direction. And that is why this area is negative. That area is negative. Until reaching the point B, where he stops. Okay. The diagram shows the graph of V against T, where V, meters per second, is the boy's velocity at time t seconds after leaving A. The boy runs and walks in the same straight line throughout. So this does not deviate from equations of uniformly accelerated motion. Because for us to talk about uniform acceleration, the path has to be straight. The path has to be straight. For us to talk about those three equations, find the distance AC and AB and AB. So I believe there should have been a value here. Let me just pause this video and check on that. So I have made those corrections. In fact, this value here was not 10, it was 7 meters per second, and this is -4. So let's see, what kind of situation are we talking about here? So what is the situation? A boy starts from point A. Let's say this is point A. Runs like this all the way to point B, pauses there for 5 seconds, and then walks back like that. So this he runs and then walks. The diagram shows the graph of v against t, the boy's velocity at time t seconds after leaving A. The boy runs and walks in the same straight line throughout. Find the distances AC and AB. Okay. He runs from a point A to a point C. So let's get this straight. He runs from a point A to a point C. He pauses at C and then walks back towards A, reaching the point B. So this is point B. So this is where he is finally. So the diagram shows, all right, we are required to calculate the distance AC from A to C. It's given by this area here, which will be 70 meters. From A to C is 70 meters. How do I get that? 10 times 7. AB. AB. Now, the distance from A to point B, I need to know this. And CB is this one here. So this area represents the distance from A to point C. This area here represents the distance from C to point B. Like that. And it is 15 times 4, which is 60. You can see this is 15 and this is 4, 60. The negative sign here signifies that it is in the opposite direction. It is the opposite direction to the distance which we are taking positive. It is in the opposite direction. So he runs 70 meters to point C, then he retraces his path and moves 60 meters in the opposite direction. So the distance from A to B is just 10 meters. 10 meters. So this one is 70 and this is 10. That's the way I view it. Now, we are asked to sketch the graph of x against t, where x meters is the boy's displacement from A. Show clearly the values of t and x when the boy arrives at C, when he leaves C, and when he arrives at B. So let's appreciate the fact that when he starts from A to point C, he runs with uniform velocity. So when we are asked to draw a velocity time graph, because that is what we are being asked, not a displacement time graph for uniform velocity, we must realize that that is a straight line. That is a straight line. So, again, I've got to make a few corrections here. Just pardon me. How do we represent uniform velocity on a displacement time graph? Uniform velocity is represented with a straight line. The straight line. So for the first 10 seconds, this line will be straight like this. Straight line. And he covers a displacement of 70 meters and then stops, is not moving, so the velocity is 0. So since the velocity is 0, this one will be horizontal. So this point A to point C remains at point C and then runs back or moves back. When he is moving back, the velocity will have a negative sign, but it is uniform. He comes back in the next 15 seconds. So he walks, but the distance he walks is 60. So how do I get this? Because his displacement is just 10 meters. So he must be at some point here. And that is when I draw a straight line like this, ensuring that now he's at point B at displacement of 10 meters from point A. So this must be 10. So this must be 60. And that is what happens. And you can see his velocity is going to be negative. So that is how you get all the values that you need. This question was testing, are we able to extract a displacement time graph from a velocity time graph? And they moved step by step. When we see a displacement time graph, we are supposed to recall that the gradient represents velocity. So from the previous question, we are supposed to see that the velocity is uniform. You can see this velocity here is uniform. Of how much? 7 meters per second for 10 seconds, covering a displacement of 70 meters. So having been told that the gradient must be straight, this line must be straight. I'm sorry, mine appears crooked, but when you're drawing your sketch, you will use a ruler to draw that. It must be straight, showing you that the velocity is uniform. And indeed, if I divide 70 by 10, I get 7 meters per second. And then he remains at point C, this is point C, and then walks back. Here he's walking back for the next 15 seconds. But he doesn't walk back to the starting point. He stops at point B, which is at a displacement of 10 meters. And that's all about question 3. Okay, let's look at question 4. Now, what are we given in question 4? We are told that the top of an inclined plane is at a height of 0.7 meters above the bottom. A block of mass 0.2 kilograms is released from rest at the top of the plane and slides a distance of 2.5 meters to the bottom. Find the kinetic energy of the block when it reaches the bottom of the plane in each of the following cases. The first case is when the plane is smooth. The second case is where you're given it is rough, and the coefficient of friction between the block and the plane is given as 0.15. So I have drawn an incline that we can use for the first case. So let's look at this first case here. So we want to find the kinetic energy of the block when it reaches the bottom of the plane in this case. This top of the incline is at a height of 0.7 meters. So here it's got gravitational potential energy. It's all that gravitational potential energy which is changed to kinetic energy at this point. So EK at this point is easy to calculate because it will be equal to the E potential that it had up there. And if I know the mass of the object times the gravitational field strength times the height, I'll be able to work out the kinetic energy at this point. We're given that it is 0.2 kilograms. The value of G is 10 Newton per kilogram. And the height is 0.7. Let's see what that one gives us. That will be 2 times 0.7. Of course, I think that one will give us 1.4 joules. 1.4 joules. And that was not so difficult. Just using energy consideration. How about if it occurred to you, because when we are in the heat of the exam, or sometimes when you are doing some of these questions, it might occur to you that the equation to use is this one. That you need the mass and you need the speed of the object. How about if that is the equation which occurred in your mind? What do? Again, you're right. You need to get the speed that it has at this point. Right? And you might need to do a bit of further calculations. Like, for example, we are given that the distance it slides, it's 2.5. This distance is 2.5 meters. It starts from rest. U is 0, and you want the final speed at that point. You see, you can be able to use the equation v squared is equals to u squared plus 2as in order to work out the v. In fact, you are going to leave it as just like a v. Now, what do I mean? The u squared was 0 squared plus 2 times the acceleration is a component of the g down the incline. So the a here will be equal to the g sine theta. So g is 10, or let it just remain as g, because I want to prove a point here. Sine of this angle is the opposite, which is 0.7, divided by the hypotenuse, which is 2.5. So that is what I'm going to use here. So g is going to be equal to 10. I mean, the acceleration will be equal to 10 times 0.7 over 2.5 times 2.5. If you have that one cancelling out, you're going to have this value here. So let's see what v squared gives us. It gives us 20. We multiply by 0.75 and we get 15. Remember, that is v squared. You might not want to get the square root of it, because I guess I can just put it in this equation directly here. So I'm going to have a half times the m, which is 0.2, times 15, like that. And what does that give me? This is what it gives me. It's going to give me I think it's going to give me 1.5 joules. Why is it different from here? Why is it different from here? M, G, H, and over here, because they appear, it should have given me the same value. I've seen where I made the mistake. It is the 0.75. Here G is G sine theta is G times sine theta is 0.7, okay, not 0.75, divided by 2.5. So this one should have given me 14, and that is the 14 I should have put here to give me 1.4. So either way, you can see it will give me the correct answer. Here, what is required is confidence. Once you think about an idea, a concept that you're going to use, because like I've said, it may occur to you that the equation to use for kinetic energy is this one, because that is what occurs in your mind. So you ask yourself several things. I've got the mass. Do I know the speed? No. So you set out to calculate the speed. You can use equations of uniformly accelerated motion, and you're going to get it all the same. Another student may use energy considerations. Now here you must be careful. Sometimes the examiner gives you the direction to follow, wants you to follow a certain direction. The examiner may even tell you, using energy considerations, calculate blah, blah, blah. You've got no option other than use the concept of energy. Or the examiner can craft this question in such a way that the only method that will work is a particular method. So you need to know more than one method of solving a question. But like I said, any method that you think about, stick to it, and make sure that during practice you understand it so well that when it comes to using it, you've got no doubt that you've not left out anything. So let's go to the second part, where now we are given the coefficient of friction between the plane and the block. So in the next slide, I can now work out part 2, where there is friction. So the block is here. There is some frictional force which is acting on the block here. There's some frictional force. And that frictional force can be given by mu r. Mu is 0.15. How do I get r? R is the normal component of the contact force. R there. How much is it equal to? Remember what we have discussed in one of the questions in this paper. And we have said that most students normally think that R is equals to the weight of the object, which is mg. That is true if this is the case. This is mg, weight of the object, and this is r. This will be true. But the moment we incline this surface, this r is no longer equal to mg. It is equal to this component of the weight in this direction. So you've got to resolve. You know the weight was like this. And this angle is the same as the angle that the incline makes with the horizontal. This angle here, theta, is equal to this angle. And since this is the weight, this, by the way, is a vertical line, this will be the weight cos theta. So that is how we get r. So in this case, it will be the weight, the cos of theta. This is, again, this one was 0.7. This is 2.5. Let me see whether I can get the adjacent, an exact value of the adjacent. This distance here, this one here, should be equal to the hypotenuse, 2.5 squared minus 0.7 squared. Let me see whether I can get an exact value. So 2.5 squared minus 0.7 squared. I hope you do understand why I'm doing that. Then I find the square root of the answer and I get 2.4. 2.4. So indeed, I can get an exact value of the cosine of theta, which is 2.4, which is the length of this line here, divided by 2.5, which is there. So 2.4 divided by 2.5 will give me the cos of theta. Let me see, did I get the mu? Yes, I got the mu, which is 0.15. Have I gotten the r? The r will be mg. Mg will be 2 times 10, then times 2.4 over 2.5. So this is not the value of r. The value of r is supposed to be 2 times 10 times 2.4 over 2.5 mg cos theta. Mg cos theta. So let's just work out that frictional force. So 0.15 we multiply by 20, multiply by 2.4, and we divide all that by 2.5, and we get 2.88. 2.88 newtons. So that is the frictional force. Let's now, you see the presence of this friction force here, it's going to ensure that the kinetic energy here is less than the kinetic energy we had in part 1. Remember, the kinetic energy here that we had in part 1 was 1.4 joules. Was 1.4 joules. So now I think there is a problem here. There is a problem here. This should have been 0.2. The mass was 0.2 mgh. Mg cos theta. M is 0.2, g is 10, cos theta is 2.4 times that. So this one is supposed to be 0.288. I'll tell you how I have been able to quickly check that 0.288. You see, if it is 2, I multiply it by 2.5, it's going to give me something almost like 4 or 5 joules. There is no way the work done against the friction can be greater than the kinetic energy the object would have here if there was no resistance. There was no way that one would be the case. You should be able to do such mental checks, and it helps you to even counter check your answers as you go along because you are using certain principles. You see, the moment I get the friction force being equal to 2.88, and then I multiply that friction force of 2.88 by the distance covered in moving a distance of 2.5 meters, I get 7.2 joules. That the work done against the resistance 7.2 joules. That object would not even be able to reach the bottom of the incline there. It will not even be able to move if that was the amount of friction. It goes against the logic of what we expect the friction force to be. There is no way the friction force can be greater than the force which is trying to move it. There is no way the friction force can be greater than the force which is trying to move it. What do I mean by that? You see, this object here wants to slide down the incline here. And so the force which is trying to move it is mg sine theta. Let's see what mg sine theta gives me. M is 0.2, g is 10, sine theta is 0.7 divided by 2.5 and that will be like 2 times 0.7 divide by 2.5, 0.56, 0.56 newtons. You see, if I left the friction force to be that odd value that I had gotten here when I made the mistake of using 2 kilograms here instead of 0.2 kilograms, I got 2.8 newtons. You can see that the friction force would have been greater than the force which is trying to move it down the incline. And I'm telling you here that there is no way friction force can be greater than the force which is trying to move it, unless we are considering a completely different situation, like when we are looking at free fall, when the parachute just opens. Here I'm talking about a completely different situation, which is not even tested in Mechanics 1. It is tested in physics. So if you are taking physics, you will be able to understand that this. During free fall, when the parachute opens, the frictional force is greater than the force which is trying to move the parachute downwards. So when that happens, it's because the physical structure of the parachute has changed. When that happens, when the friction force is greater than the force which is trying to move it, the object is decelerated. When that happens, when the friction force is greater than the force which is trying to move it, the object slows down. It is decelerated. But here, this one is not such a situation. The coefficient of friction is not changing. The friction force is not changing. So, having said that, I think you're getting the point that having some other knowledge of this particular situation, I have used 2 situations. I've looked at the friction force that I had gotten, 2.88, against the force which is trying to move is 0.56, and then I've said that one is not possible. Again, when I look at a value of 2.8, which is approximately 3, I multiply it by a distance of about 2, I get 6 joules. It will be greater than the amount of energy which I had gotten here. Again, that one is not possible. It means the object will not move in the first place. So, such things, they help me to check my answers very, very fast. So, at this point, where am I leading to with the friction force? It can lead to a situation whereby I know there is a force of 0.56 tending to move this object downwards. There is friction force of 0.288, so there is a resultant force of a certain magnitude. For example, now I know that the friction force is 0.288. I can come here and say a resultant force on that object is equals to ma. And why would I get the acceleration? I want to get the acceleration so that I can get the speed that object at this point, and using the speed, I can get its kinetic energy. Again, these are ideas which are occurring in my mind because there are 2 forces acting on this object, the driving force and the resistance. So the m is 0.2 times the a. Now this resultant force will be the driving force, which is 0.56 minus 0.288. Now this makes a bit of sense. So 0.56 minus 0.288, I get 0.272. I get 0.272. Now that one, I can divide that answer by 0.2. Now to get the acceleration of 1.36. 1.36. meters per second squared. Now let me work out the acceleration of this object, or rather the speed the object has at this point. V squared is going to be equal to u squared plus 2as. It starts from rest. There's these two here. There is 1.36. There is 2.5. And v squared will be, I already have 1.36, my calculator. I'm going to multiply that one by 2. And then I multiply again by 2.5. And I get 6.8. 6.8. It's v squared. So in order to get EK, which gives me a half mv squared, I do not bother to find the square root. I simply use it as it is. The mass is 0.2 and the v squared is 6.8. Let me see what I get. So I've already got 6.8 there, multiplied by 0.2. Then I divide all that by 2. And I get 0.68. 0.68 joules. That makes sense. So that is one of the methods that I can use to solve this question. What would be the other method? I already know the energy it has, the kinetic energy it has at this point if the plane was smooth. I can decide to calculate the work done by frictional force. Work done by friction force is going to be equal to the frictional force itself, which is, by the way, it will have a negative sign. Do you know why it has a negative sign? Friction force points that way, but the object is moving right in the opposite direction. So I've got to resolve friction force in this direction by doing 0.288 cos 180 so that I can change its direction to point in the direction in which this block is moving. When I do that, cos 180 becomes minus 1. That minus 1 is what brings everything here. So I'm going to have that friction force, which is 0.288 times the distance covered, which is 2.5. Let me see what that one gives me. 0.288 times 2.5, and I get 0.72. This is the amount of work that will be wasted, or that must be subtracted from the potential energy here, so that the resultant will now give me the kinetic energy that the object has here. Remember, in part A, we said all the potential it had here is converted to kinetic energy at this point. That is if it was smooth, but now it is rough. Some of that gravitational potential energy is converted to heat due to friction. It's converted into this. The result is what we remain with as kinetic energy. So EK is going to be equal to what we would have got, which is 1.4, then I subtract what we have converted into heat. So I get the answer to part 1, I subtract that. So I'm going to get 1.4 minus whatever answer I got there, I get 0.68. 0.68 joules. And you can see that a student using this method or this method, they arrive at the same answer, so long as you put your working in such a way that everything is quite clear. And that is how you work out question number 4. Let's look at question number 5. And here we have question number 5. We are given a particle P moves in a straight line that passes through the origin O. The velocity p of p at time t seconds is v meters per second squared, where v is equals 20t minus t cubed. At time is equals to 0, the particle is at rest at a point whose displacement from O is negative 0.36 meters. So let's look at the situation that we're talking about here. Here we've got our origin. It moves in a straight line that passes through the origin O. So here, the origin O. The velocity of particle P is given by this expression. At time is equals to 0, the particle is at rest at some point. Let's assume that any movement to the right is positive. Is positive. So it means that I start measuring my distances from here, 0, 1, 2, 3, 4, 5. But if it was behind in this direction, then I count it backwards, and that is where the object was. It is 36 meters, 36 meters behind. This is where it is, and it's moving like that, and it is at rest. The particle is at rest at a point whose displacement from O is that much, because any displacement from this line onwards to the right is positive. Anything in that direction, negative. So having understood that, let's see what happens. Find an expression for the displacement of P from O in terms of T. At this point, I'd like you to recall this. When we move from displacement x to velocity v to acceleration a, we are differentiating. When we move in the opposite direction, we are integrating. So what is it that we've been given? We've been given the expression for velocity as a function of time. Velocity as a function of time, written like that, is 20t minus t cubed. If I differentiate it, I will get acceleration, but I want displacement, so I must integrate. So this is the same as what I did, dx dt. X is the displacement. So let me collect the variables. Okay, starting with the dx. Dx is going to be equal to 20t minus t cubed, everything here dt. This process is called separating the variables. So I'm going to integrate this. I'm going to integrate this and this with respect to time to give me x displacement. When I integrate here, I get 20t squared. I must drop this 2 here. Minus t raised to power 4. I must drop this 4 here. Plus a constant c. That is the expression for displacement as a function of time. Now, what is it that we are told when time is 0? When time is 0, the displacement is minus 36. So, and I put a 0, 0. When I put 0 here, this one becomes 0. I put 0 here, this one becomes 0. And I remain with c. So, that implies that my c is minus 36. And the expression for the displacement from P, from O in terms of T is x is going to be equal to 10 t squared there, a quarter t raised to power 4 minus 36. That is the first part. That's how we do that. Second part, find the displacement of P from O when T is equals to 4. That one is very easy. Part 2, X when T is equals to 4 seconds will be equal to, this one will be 10 times 4 squared, which is 16, minus 1 over 4. 4 times 4 raised to power 4 minus 36. Of course, here I'm going to find that this one will be equal to 160 minus, that appears to be like 4 cubed, because one of the 4's cancels out there. So 4 cubed, I get 64, and I have 36. So I have 160 minus 64 minus 36, and I find it is 60. That is how I get part 2. Part 2 is very easy. I just need to substitute t is equals to 4 seconds into this expression, and that's what I get. And then finally, find the values of t for which the particle is at O. Values. Look at the plural. So there are 2 values of t for which the particle is at the origin. When it is at the origin. When it is at the origin, it means that the displacement is 0. The displacement is 0. So if the displacement is 0, I'm going to take this expression x and say that x is 0. And that one is equal to 10 t squared minus a quarter t raised to power 4 minus 36. Everything is equals to 0. Let me multiply throughout by 4, not get 0, going to be equal to 10 t squared minus t raised to power 4, 36 times 4, it's 144. 144. No, this one is actually t raised to power 4. T raised to power 4. So at this point, I can either factor out or say, let t squared be equal to x, or be equal to something else. Let me not use x because I've already used x there. Can say let t squared be equal to, let's say, w. That will mean 0 is equals to 10 w minus w squared minus 144. And then I'm going to rearrange these and say w squared minus 10 w. Of course, I've moved this one to the right, so this one becomes negative and the other one becomes positive. 144 is equals to 0. And this one is a quadratic function. You can see this one and this one, and I'm able now to solve that quadratic function. Appears a little bit lengthy. It is for 3 marks. Yes, I think this is the method that I would try to use for working out part 4. The moment you solve for w, you'll go back and substitute it here. And you'll find the 2 values for t. Now let us look at question 6. In this question, we are told that a car of mass 1200 kg travels along a horizontal straight road. The power of the car's engine is 20 kilowatts. The resistance of the car's motion is 400 newtons. Part 1, we are required to find the speed of the car at an instant when its acceleration is 0.5 meters per second squared. Now let's straight away go to this first part. I've created some space here where I can be able to work out each question separately so that it is clear to us all. Now I want to focus on something that I've said in some past videos, when to use the equation power is equals to force times speed. This equation here, power is equals to force times speed. This will be the driving force, while this should be the constant speed that the object should have. So this equation is used when the speed of the car is constant. But in this case, the speed of the car may not be constant. In fact, it is not, because you can see the car is accelerating. But we can use this equation at an instant of time. At an instant of time when something is happening. What is this instant of time? Let me go back to the previous space here, because I want us to look at that situation clearly. This is the car. There is some resistance. We are going to represent it by FR. And then the engine itself is exerting a certain driving force. Definitely, this vehicle is accelerating. So, this driving force will be the one which is obtained from power is equals to driving force times the speed. In other words, the driving force is power over the speed. The resistance is obviously 400 newtons. There is no problem with that. This is the mass of the car, and this is the acceleration that the car has at that instant of time. So when we use the equation F is equal to ma, F, which is the resultant force, is equal to ma, we realize that this resultant force is obtained by the driving force minus the resistance is equals to ma. And it is at this point that we substitute this driving force by the power divided by the speed. At that instant of time, this is what we have. So that is the equation that we are going to use. So remember, this equation is used in two instances. When the speed of the car is uniform throughout, or at a particular instant of time when we are given a certain speed. At that instant, we can be able to use that equation because the driving force is producing a certain amount of force which produces that acceleration at that particular speed, and at that instant we can use that equation. So that is the equation we want to adapt in our calculation here. So like we have said, power over that speed minus the resistance will be equal to ma. If we substitute, the power is 20,000. The speed, find the speed of the car is what we want, minus 400 is equals to ma. That will be 1200 times 0.5. So we can simplify this. Apparently here, I don't seem to have much space. So I can have my 20,000 there over the speed is equal to, on the right hand side, I'm going to have 600. 600 plus 400, I'm going to have 1000. And obviously the speed will be equal to 20,000 divided by 1000, and it will be 20 meters per second. So that is how we get the speed here. So here, that speed will be 20 meters per second. It's just as simple as that. Show that the maximum possible speed of the car is 50 meters per second. The idea here is maximum speed. Again, maximum speed. You're going to encounter this concept of maximum speed in future in so many past papers. So why don't we understand what it means? At maximum speed, the acceleration of the car is zero. Is zero, because once the speed reaches that maximum value, then it will move in a straight line with the same speed throughout. So again, I'm going to use the same expression here. The power is 20,000 divided by that maximum speed minus 400 is equal to MA. A is 0, so on the right hand side it will be 0. So again, we are going to rearrange this, and we are going to show that this 20,000 divided by V is equal to 400. And if we rearrange that, we're going to see that V will be 20,000 divided by 400. And we'll be able to see that this one gives us this 50 meters per second. Just as simple as that. So what do you take from this video? So far, so good. There are two things you need to take away. When to use the equation power is equals to driving force times speed, and the concept of maximum speed. Especially that applies to objects which have engines, which have got driving forces. Okay, let's look at the third part. The work done by the car's engine as the car travels from point A to point B is this. So we can straight away look at this. The work done by the driving force is 1,000 or is 1,500 kilojoules. So it is that much. Now, when I'm looking at this type of question, there are four things I'm interested here. Work done by driving force, and then work done by the resistance, and then gain in kinetic and gain in potential energy. I want to make this question to be as simple as possible. So they've given me one of those four things that I will be looking for. Work done by the driving force. Is there any work done by resistance? Of course there is. Given that the car is traveling at its maximum possible speed between A and B, find the time taken to travel from A to B. Given that the car is traveling at its maximum possible speed. What is the maximum possible speed? It is 50 meters per second. So I might want maybe to calculate the distance AB. Might want to calculate the distance AB. Since I know the work done by the driving force, the gain in E kinetic is 0. Why? The car's speed is constant. Let's look at the gain in potential. Again, it is 0 because this road is horizontal, a horizontal straight road. I'm left with the work done by resistance. This will be equal to the resistance force, all right, and it must have a negative sign because I'm talking about work done by that force. Remember what we did in the previous question. We realized that maybe here it's important for me to outline this once again. Here is the object. It's moving in this direction. Resistance is acting in this direction, and it covers a certain distance d in this direction. You can see that when we calculate work done by a force, the force and the distance must be in the same direction. So in this case, I'm forced to resolve this force in the direction of the distance. And you can see they are separated by 180 degrees. So I'm going to get FR cos 180 degrees times D. The cos 180 degrees is -1. So that is what makes the work done by resistance force to carry a negative sign. So I immediately put that negative sign here. I know how much it is. It's 400 times D. And now I can put these 4 components in a standard equation, which again, I've explained this equation so well in my Udemy course. So ensure that before you leave this video, you have visited that site and seen some of the free videos I have there. And perhaps by you enrolling in the course, you'll be able to learn so much. It will just take you about 7 hours to complete the whole course, and you have all the concepts that you need for Mechanics 1. So let's put everything together. Work done by external forces, which means work done by driving force, plus work done by resistance, because these are external forces, is equals to the gain in potential energy plus the gain in kinetic energy. So in this form of questions, sometimes some of these questions have got so much wording that you want to distill everything down to just a few key concepts. When you realize that the question is dealing with work done, power, speed, resistance, and so forth, it calls for you to calculate each one of these 4 concepts. And let's see how easy this is going to be. This, we've already been told that it is 1,500,000. This is negative 400D. And on the right-hand side, we've got 0. Of course, you can see that D will be equal to 1,500,000 divided by 400. I'm running short of space here, but not to worry because everything is taken care of. So I'm going to divide 1,500 1,500,000 because that is what 1,500 kilojoules stands for. I divide that by 400 and I get it to be 3,750 meters. And like I said, if this car is traveling at constant speed, then time is given by by the distance itself divided by that constant speed. The distance, I've worked it out to be 3750, and then I divide by 50 over here. So all that I divide by 50 meters per second, and I find it is 75 seconds. It's just that simple. Crowded, fine, but I hope you've been able to follow. Again, let me quickly review the takeaway from this video. Like I said, it's very important that you understand what it is that we're talking about. Number one, when do we use this equation? Driving force, driving force is power divided by speed. Two situations. Either when the motion of the car is constant, when the speed of the car is constant throughout, or at an instant of time. This is such a situation. So you'll be looking for this word. Certain words are not just used in these examinations for the sake of it. They are supposed to point you in particular direction. Number two, the idea of the object having maximum speed. It means that the speed is going to be uniform, and therefore the velocity will be uniform if the object is moving in a straight line. When that happens, the acceleration is zero. If the acceleration is zero, resultant force is zero. And that is why the right-hand side was zero, because mass times zero is zero. The third part is the need to start thinking in terms of these four components. Work done by external forces is equal to gain in energy. A very simple concept. Work done by external forces is equal to gain in energy of the system. What two external forces do we deal with in mechanics? Number one, the driving force. For example, if an object has an engine or it is being pulled by a cable, there must be a driving force. That driving force covers a certain distance. So we can talk about work done by the engine, work done by the driving force. It's all the same. Now, if this car or object is experiencing some resistance, there must be resistance to the motion of that object. So that resistance, which acts in the opposite direction to the direction that the car is moving, must be doing work on the object. And because the force and the distance covered in opposite directions, we resolve the force in the direction of the distance by use cos 180 degrees, and that is what makes the work done by resistance to carry a negative sign. However, we still maintain the wording work done by resistance in our calculation, work done by resistance. The examiner will use the term work done by resistance. It makes no difference. It means the same thing. Remember, when you calculate your work done by friction or by resistance and it carries a negative sign, when you call it work done against the resistance, you ignore the negative sign. It's more like acceleration and deceleration. When you work out acceleration and you find that it got a negative sign, what do you call it? You call it deceleration, and you drop the negative sign. Very simple. Now, very quickly, you will have to observe, like I told you, these words are not just used for the sake of it. This one is a horizontal road. Why didn't they just tell you it is a straight road? Why do they mention horizontal? It's for you to realize that that object does not gain any potential energy, and therefore the gain in potential will be zero. Why did they have to tell you here that it's traveling at the maximum possible speed? So that you can realize if the speed is constant, the gain in kinetic energy is zero. So when it comes to putting these four components together, the work done by external forces being equal to the gain in energy of the system, you will have to just pick those individual parts and fit them into that equation. That equation works all the time. And I'd like maybe a student out there, just challenge me and ask me, or give me a question where that equation does not apply. When do you know when to apply that equation? When the question has got power, there is some driving force, there is some work done by resistance, and so forth. Especially vehicles and objects with engines. That expression always works, it never fails. And at that point, let's go to question number 7. And here we are in question number 7. What are we told? We are given this. There is a particle P which is projected vertically upwards from a horizontal ground with a speed of 30 meters per second. At the same instant, another particle P2 is projected vertically upwards from the top of a tower of height 25 meters with a speed of 10 meters per second. Find the time for which P1 is higher than the top of the tower. And we are going to start with that. Let me go to the first situation. So here I've got particle P1, which is at the bottom of the tower. And both of them are projected vertically upwards at the same instant. I tried to create a simulation of this so that you can be able to see what is happening, but apparently I never completed this. So that is what I think happens. At some point, they will have to meet. I don't know whether they will meet. I don't know whether this object reaches maximum height, comes and bypass the height of the tower and falls. But what I'm sure about this is that it will reach maximum height and then fall back. Let's answer the first part. There is a time when this object is, you see, it moves from here. It has been fired vertically upwards with a speed of 30 meters per second. And the time at which it is just above the tower will be this one, that is T1. And then it continues to move, reaches maximum height, and then falls back here. There are those two times. T1, which is up to that point, and then T2, which starts from here, moves all the way to maximum and comes back here. And then the difference between the two, is what gives us the time that that object is above the tower. I'm going to repeat this because it's very important. There are two times when the object is exactly 25 meters above the point of projection. One time is when it is on its way upwards. The other time is when it is on its way downwards. What is time 1? Time 1 is when it moves from here all the way to that point. What is time 2? Time 2 is when it moves from here all the way, reaches maximum point, and then comes back here. You can see that by subtracting time 1 from time 2, I will get the time it takes to be on top of that tower. So this question is simply worked out by using S is equal to UT plus, of course, I have AT squared. The displacement of the particle in both cases is 25. U is 30. Of course, T. Minus comes from the fact that I'm going to use 10 here. And when I use 10 multiplied by a half, I get 5 T squared. I hope you have realized how worked out that. I've just replaced A with minus 10 because the object is moving against vertically upwards. Now to get this simple expression, divide this expression by 5 throughout because 5 appears to be the best value to divide with here. I get 60 and then minus T squared. So my expression becomes T squared minus 6T plus 5 is equals to 0. I wanted to get a quadratic equation. Of course, I can solve this using quadratics. I'll get two values of t, and once I get two values of t, I find the difference between them, and everything is solved. When I do a times b, should be able to get 5. When I do a plus b, should be able to get -6. What are these two numbers when this happens? Of course, it must be 5 and 1. It must be 5 and 1. How is that? Think about multiplying 5 by 1, I get 5. How about if they are -5 and -1? I multiply the two, I get 5. I add the two, I get -6. So those are the two numbers that I need to put there. So I'm going to say t squared minus 1t plus -5 plus 5 is going to be equal to 0. So let me put brackets here. T squared minus t minus 5t minus 5. In order for me to put brackets like that, I'm going to get 0. So t into t minus 1 minus 5 outside there, t minus 1 is equals to 0, and t minus 5 into t minus 1, I get 0, and the first value of t, t1, is 1 second, and the second value of t is 5 seconds. Makes sense that it took 1 second to cover this 25 meters, and then it took 5 seconds to cover this distance all the way to maximum height and back to here. So the time for which it is above the tower is that time for which P1 is above the tower is 5 minus 1, which is 4 seconds. So there are 2 times. Now we are again asked for the velocities of the particles at the instant when the particles are at the same height. They are at the same height. What does that mean? If they are at the same height, let's assume that P2 is somewhere around here and P1 is somewhere around here. They actually are the same height. It does not matter the direction in which they are moving, but as far as the ground is concerned, they are at the same height. So let's assume that such a position is the one that we are talking about. Let's consider the displacement of particle P2, because this is P2, this is P2, and this is P1. Let's consider this to be equal to h, for example, h. So for particle P, for it to cover displacement h, I'm going to say S, which is h, is equal to ut. Its u is, it was fired upwards with an initial speed of 10 t minus this one here. Of course, that one will be 5t squared. Let's look at for particle P1. It will be 25 plus h. So 25 plus h because that is its displacement. It's going to be equal to ut, which is 30t, again minus 5t squared. I've got two expressions that I can be able to solve simultaneously. How do I do that? So I've got the two expressions and I want to find the difference. So let me subtract upwards. 25h plus minus h, I am going to get 25. 30t minus 10t, I'm going to get 20t. Of course, this minus that, this one minus that, it just cancels out. So I'm going to get my t to be equal to 25 divided by 20. 25 divided by 20, and this will be the time. 25 divided by 20, 1.25. 1.25 seconds. Of course, it will be after P1 has reached the top of the tower, and it will be exactly where I've shown it. At least above the tower, not below. How do I know that? It's because P1 took 1 second to rise to be above the tower. 1 second. So 1.25 seconds, it's obviously above. And of course, it took 4 seconds to be above this tower. So we are safe as far as that is concerned. Let's look at part 3, the time for which P1 is higher than P2 and is moving upwards. The time for which P1 is higher than P2 and is moving upwards. So I might want to, how long does this particle, the particle P2, take to reach maximum height? Since it was fired with 10 meters per second, it takes 1 second to reach maximum height. How do I know that? I can use V. I can use the equation V is equals to U plus AT. Let's see the time it takes to reach maximum height. It will be V, which will be 0, minus 10, divided by minus 10. It will take 1 second. So if I do an analysis, when P1 has reached this point on its way upwards, then P2 has already reached its maximum height and it's on its way downwards. So when they meet here, P1 is on its way upwards. And P2 is on its way downwards. That is when they meet. So what does my question talk about here? The time for which P1 is higher than P2. So at least they must meet. P2 is on its way downwards and P1 is on its way upwards. So they meet. P1. So the moment after that particular instant, P1 is higher than P2. It's higher than P2 and it's on its way upwards. So how long does P1 take to reach maximum height? I can also use the same equation V is equals to U plus AT, in which case the V for P1 will be 0. This one will be minus 3. Of course, minus 30. V minus U and minus 10. So it takes 3 seconds to reach maximum height. Since it takes 1.25 seconds for it to meet this one. Okay, let's put a few concepts together because we can see that the writing space has become messed up. But I hope you are still following. P1 takes 3 seconds to reach maximum height, while P2 takes 1 second to reach maximum height. They meet after 1.25 seconds. So, after 1.25 seconds, P1 will be higher than P2. And since it takes 3 seconds to reach maximum height, the time we are talking about here, this delta T here, for which P1 is higher than P2 and it's moving upwards, will be equal to the time that P1 takes to reach maximum height, which is 3, minus the time when they meet, 1.25, and this will be 1.75 seconds. Now, when I'm working these questions, I don't work these questions and then once I have perfected the answer, I come and record this video. No, that is not what I do. I behave just like you when you're meeting this question for the first time. That is why I keep on running through. This method will work, this one doesn't work, just like you would do, because I want us to work together. I want you to see that everybody out there struggles with this question, but we end up getting the questions correct after being sure of certain concepts, after being clever enough to look for clues that the examiner keeps on throwing our way. For example, the concept of particles which are moving under gravity, which we call free fall, and sometimes we do include some air resistance. This type of question is very common. Situations where we include air resistance is like the paper I did the other day of May, June 2003, where the two particles were tied with a string, and when the top string was cut, when S1 was cut, they continued moving downwards, but the air resistance on each one of them was different, keeping the tension in the string not being zero, so the string does not become slack. So that type of question is common. And you realize that in each one of these questions, there are some things that are pointing out and telling you that these things repeat themselves over and over again. In my next paper, which will be May, June 2005, you'll be able to see some of the things I'm telling you here, how they repeat themselves. And by the time you do maybe the 4th or the 5th paper, you've already gotten that kind of motion. This video, they are long, all right. They are not short videos. They are meant to develop a certain level of patience in you as a problem solver. Avoid the quick fix kind of situations, which I've seen so many students engaging in. They want a quick fix, a quick way to working out a question, some kind of shortcut. Avoid that kind of path, because if you are to take shortcut to passing an examination and you don't put in the necessary work that is required, the necessary hard work that is required, you will definitely find these questions very hard. And chances are that you may not succeed in your exam if you look for shortcuts. Don't look for shortcuts. Have the patience to go through these long videos, and I've made it possible for you to be able to use the scroll bar at the bottom for the video. When you hover the cursor over that bar, you'll be able to see the timestamps that I've put there so that you can quickly go to a particular question. of your choice. But like I say, I will always appreciate if you go through the whole video. I'll also appreciate if you go ahead and leave a comment. Maybe there is some mistake that I made somewhere. If you just observe that, just let me know, because we are human beings. We are likely to make mistakes. Like I told you, I don't work these questions well in advance and then I record the video. No, I just get a past paper and start out straight. The only thing I do is that I prepare slides for every question. But for as far as the answers are concerned, you have seen I'm using the calculator together with you. So go right ahead, leave a comment below the video, and if this is your first time on this channel, consider subscribing so that we can solve these questions together. I will also appreciate if you share these videos with your friends so that the number of people who are seeing this kind of problem solving increase and we are able to exchange ideas. You can even be able to compare what you have learned here with what they are saying about my ways of teaching. Otherwise, I want to thank you for being patient with this long video, and I hope you will come again for the next video, which I'm going to release after maybe a day or two for the May-June 2005. Bye-bye.